quantum chromodynamics.
QCD.
Yeah, QCD.
Right.
You sent us a ton of sources on this, articles, research papers, even some lecture notes.
Wow.
So you are definitely trying to wrap your head around this topic.
It sounds like it.
It's a pretty dense one, I'll admit.
Yeah.
But luckily, we've got you here.
Here to help.
So
yeah.
let's just start off with, like, what even is quantum chromodynamics?
Well, I think the easiest way to think about it is like you look around, everything you see, stars, trees, rocks, phones, whatever it is made up of atoms.
Mm-hmm.
And you go deeper into that atom and you got protons and neutrons in the nucleus.
Okay.
But even those are not the most fundamental building blocks, right?
Right.
So you go down even deeper and you get to these things called quarks.
Okay.
And QCD is the thing that describes how those quarks are bound together by this thing called the strong force to make up all that matter that we see.
So it's kind of like the rule book for how matter is made.
Exactly. Yeah, and the interesting thing about it is that when you think about the other fundamental forces like electromagnetism or gravity, those forces get weaker with distance, right?
Okay.
But the strong force is completely different. It actually gets stronger the further apart the quarks are.
Really?
Yeah. So it's kind of like a rubber band. The more you stretch it, the harder it is to pull apart.
That seems kind of counterintuitive.
Yeah, it's definitely not what you expect, but that's what makes it so interesting.
So if it's getting stronger as you pull it apart, how do they even stay together in the first place?
Well, that's where these things called gluons come in.
Okay.
And gluons, they act as the glue that binds these quarks together.
Okay.
And unlike photons, which carry the electromagnetic force, right?
Right.
Gluons themselves, they carry something called color charge.
Wait a minute.
Yeah.
Color charge?
Yeah.
Is this like actual colors?
No, not actual colors. It's more of a way for us to visualize it.
Yeah.
But basically, quarks come in 3 different colors: red, green, and blue.
Oh.
And they have to combine in very specific ways to form these particles that are color neutral.
Okay.
Like, you know, when you mix red, green, and blue light, you get white light.
Right.
Same kind of idea.
So it's like this color balancing act
Exactly.
that's holding everything together.
That's a good way to think about it.
Okay.
And the thing is that gluons, they also carry color charge.
Okay.
And that means that they can actually interact with each other.
Hmm.
So it's not just that they're mediating a force between quarks, but they're also kind of like talking to each other and forming this complex web.
So it's like a whole conversation going on.
Kinda.
Down there.
Yeah.
Between these colors.
It's definitely a very different picture than we get with other forces.
Yeah, so we've got these quarks with their color charges. Gluons are acting like this super strong glue, and then this weird relationship between distance and strength. Sounds like we're juggling magnets.
Yeah, kind of.
That's attracting and repelling each other all at the same time.
It's a very dynamic system for sure.
And because of all of that, we never actually see individual quarks.
Exactly, right.
They're always like confined in these bigger particles.
That's one of the key features of QCD. It's called confinement.
Okay, so how do we even know they exist if they're always locked up?
That's a great question, and it's actually one of the big challenges for physicists.
Okay.
But we've actually come up with clever ways to kind of see inside these particles.
Okay.
And one of the most important experiments is called deep inelastic scattering. And basically what we do is we take these really high energy electrons and we smash them into protons.
Yeah.
And by looking at how those electrons scatter, we can get a glimpse of what's going on inside.
That's so cool.
Yeah. It's pretty amazing.
So it's like a very high-tech game of billiards.
You could think of it that way, yeah.
Okay, so that's how we know that they exist. But you mentioned that the strong force actually gets weaker as the quarks get closer together. So wouldn't that make it easier to just break them apart if they're really close together?
Well, that's where the concept of asymptotic freedom comes in.
Asymptotic freedom?
Yeah.
Oh,
and it's a very important concept in QCD.
All right.
And basically what it means is that at very, very, very short distances, like those found within a proton, quarks behave almost as if they were free particles. But as soon as you try to pull them apart, that strong force kicks in and it pulls them right back. So it's like they have a little bit of wiggle room when they're close together, but try to escape, and it's like this invisible leash.
Wow.
Yanks them right back in.
So this asymptotic freedom thing, is that what those guys got the Nobel Prize for?
You're talking about Gross, Wilczek, and Pulitzer.
Yeah.
Yeah, back in 2004, they were awarded the Nobel Prize in Physics for their discovery of asymptotic freedom in QCD.
So that was a pretty big deal.
Yeah, it was a huge breakthrough in our understanding of the strong force, and it really helped to solidify QCD as the theory of the strong interaction.
So we've covered quarks, Gluons, color charge, confinement, asymptotic freedom.
That's a lot.
My brain is starting to hurt a little.
Yeah, it's definitely a lot to take in.
But
But you're doing great.
I feel like we've just kind of like dipped our toes into this.
Yeah, we've just scratched the surface.
Okay.
There's so much more to explore.
All right, well, let's take a quick pause and come back for part 2, where we'll unravel even more mysteries of quantum chromodynamics, or QCD.
Sounds good.
All right, we'll be right back.
So welcome back to our deep dive into the quantum realm. We're going to keep going down this rabbit hole of QCD.
All right, you mentioned that gluons interacting with each other lead to some pretty crazy consequences.
Yeah, they do.
Where do we even begin to unpack that?
Well, one of the most, I guess, mind-bending ones is something called chiral symmetry breaking.
Chiral symmetry breaking.
Yeah, it sounds complicated, but it basically boils down to this.
Okay.
In a perfectly symmetrical world, right? Certain particles should have equal masses. But in the real world, we see a wide range of particle masses.
Right.
And this thing, chiral symmetry breaking, helps to explain why.
So in a symmetrical world, everything would be like the same mass.
Right, or at least certain pairs of particles would.
Okay, so how does this symmetry get broken?
Imagine you have like a mirror image of a particle, right?
Right.
In a symmetrical world, both that original particle and its mirror image would behave the same way, have the same mass.
Okay.
But in the quantum world, things aren't always that simple.
Right.
Because gluons can interact with each other. They
Right.
kind of create this background field, you could say, that affects the way quarks behave.
So it's like they're setting the rules of the game.
Exactly. Yeah. So this field, if you want to call it that,
Yeah.
it can actually distinguish between a particle and its mirror image,
Oh, wow.
which can lead to differences in their masses.
That's really interesting.
Yeah, it's kind of like one particle's playing on a tilted playing field while the other one's on a level 1. They're not going to experience the game the same way.
So that's why some particles are heavier than others.
It's one of the reasons, yeah.
Okay, but what does that have to do with the bigger picture of QCD?
Well, it actually has a lot of implications for understanding,
Yeah.
How particles interact, their properties, all of that. For example, it helps explain why pions, which are these particles that mediate the strong force between protons and neutrons, they're actually much lighter than you would expect if chiral symmetry wasn't broken.
So it's kind of like this chain reaction.
Yeah, you could think of it that way.
The gluons are interacting, it breaks the symmetry.
Right.
That affects the mass.
Yeah.
And then all of that affects how the strong force works. It's all connected.
Yeah, it all kind of feeds back into itself.
Wow.
And speaking of things that are connected, let's talk about the QCD vacuum.
The vacuum, I thought that was just like empty space.
Well, in classical physics, you might think that, but in QCD, no. Empty space, or what we think of as empty space, is actually like a boiling pot of virtual particles and fields.
Wait a minute.
Yeah.
So even when we look at like the emptiness of space, there's all this quantum stuff happening.
It's not empty at all.
That's crazy.
Yeah, these virtual particles are popping in and out of existence constantly.
Wow.
They can't be directly observed, but their presence affects other particles.
Okay.
And it affects the properties of the vacuum itself.
So it's almost like a hidden world?
Yeah, it's kind of like looking at the surface of the ocean. You don't really see what's going on underneath.
Right.
There's this whole rich ecosystem down there.
Okay, so how do physicists even begin to study this hidden world?
It's a big challenge for sure, but one tool that we use is something called lattice QCD.
Lattice QCD, okay.
Yeah, and basically what it involves is taking the fabric of space-time, right?
Okay.
And dividing it up into this 4-dimensional grid.
A 4-dimensional grid?
Yeah, like a cosmic chessboard, you could say.
That sounds pretty complicated.
It is, but this grid allows physicists to use these supercomputers to simulate how quarks and gluons behave on this lattice.
So it's kind of like a digital laboratory.
Exactly.
Where they can just run all these tests.
Yeah, and do experiments that would be impossible to do in the real world.
Huh, that's so cool.
Yeah, it's a really powerful tool.
So we can use that to study like confinement and stuff.
Yeah, confinement, particle masses, all sorts of fundamental properties of QCD.
So even with all of that, we still don't totally understand confinement.
That's right. It's still a big mystery. We know it happens.
Yeah.
We see it in experiments.
Right.
But the exact mechanism is still something that we're trying to figure out.
And you mentioned that proton spin puzzle earlier. What was that all about?
So we know that protons, like all particles, have this intrinsic angular momentum called spin, right? You might think that the spin of a proton just comes from the spins of its quarks.
Makes...
But it turns out that it's not that simple.
Okay.
For one thing, gluons themselves carry spin.
Right.
And we don't fully understand how their spin contributes to the proton spin.
Okay.
And then there's also this thing called orbital angular momentum, which is like the motion of the quarks around each other.
Yeah.
And that also plays a role.
And
to make things even more complicated, it's possible that even the vacuum itself is contributing to the proton spin.
So it's like we're trying to calculate the spin of a planet.
Yeah.
But we're not just considering the planet itself. We're thinking about the atmosphere and any moons it has, and maybe even dark matter or something.
That's a good analogy.
Wow, it's amazing how many layers there are to all of this.
Yeah, it's a reminder that even in the seemingly simple world of subatomic particles, there's just layers upon layers of complexity.
All right, well, before we get too lost in all these layers, let's take a quick break. We'll be right back to wrap up our exploration of QCD.
And we are back for the final part of our deep dive into QCD.
Back into the quantum world.
You know, it feels like we have been down such a deep rabbit hole.
It is a deep one.
All these quarks and gluons in this crazy vacuum. There's a lot to wrap your head around, for sure.
So we've talked about all these concepts, but I'm curious, what are the biggest challenges still facing QCD researchers today?
Well, one of the most fundamental questions that we're still grappling with is confinement.
Okay.
We know that it happens, right?
Right.
Quarks are trapped inside hadrons. We can't pull them apart.
Yeah, it's like those high-security prisoners.
Exactly. But we still don't fully understand the mechanism behind it.
Like we see the bars, but we don't know how they got there.
Exactly. There are a lot of theoretical models out there, but none of them have been able to give us a complete picture.
So it's kind of like the holy grail of QCD research.
In a way, yeah, it's one of the biggest mysteries we're still trying to solve.
And the QCD vacuum, that's another thing that's been blowing my mind.
Oh, yeah.
This idea that empty space is actually teeming with all these virtual particles. What are some of the implications of that?
Well, for one thing, it means that the vacuum isn't just this passive backdrop.
Right.
It's actually an active participant in the quantum world.
So it affects, like, what, the properties of particles?
Yeah, the masses and particles, how they interact with each other.
Okay.
It might even have played a role in some of the most fundamental processes in the universe, like the formation of matter in the early universe.
So it's like this invisible hand guiding everything.
Exactly. And the more we learn about the vacuum, the more we realize how important it is.
Okay, so QCD is clearly super important for our understanding of the universe.
Absolutely.
But does it have any, like, practical applications?
Oh, yeah. Definitely. It might seem like a very theoretical, abstract subject.
Yeah.
But it has real-world consequences. Well, our understanding of nuclear physics, how atomic nuclei are held together, that's all based on QCD.
Right.
And that's important for things like nuclear energy, medical imaging, even smoke detectors.
Wow. So QCD is secretly powering our world.
In a way, yeah.
That's amazing. And as we learn more about it, who knows what other applications we'll discover?
Exactly. That's the exciting thing about fundamental research. You never know where it might lead.
Like, maybe we could even harness the strong force someday.
Well, that would be incredible, wouldn't it?
Yeah, that would be a total game changer.
Imagine the energy we could generate or the new materials we could create.
It's mind-blowing to think about.
Yeah, the possibilities are endless.
Well, I have to say, this has been a really amazing deep dive.
It's been a pleasure.
I've learned so much, and I feel like I have a whole new perspective on the universe now.
That's great to hear.
And for everyone listening out there, I hope you feel the same way.
Keep asking questions. Keep exploring.
Yeah, there's so much more to learn about QCD and the quantum world.
It's a fascinating journey.
All right, that's it for this deep dive. Until next time, keep exploring.